All right, so today we are moving on to the final piece of graphing our rationals. So we're going to do more stuff. We're going to add in some degrees to my numerator and or denominator and see what that changes, okay? So a new key feature on my graph that we haven't identified yet is our x-intercept, okay? X-intercepts of the graph f are the real solutions of p of x equals 0. Well, that's very fancy for, because where do you see p of x? Over here. It's the top. So x-intercepts are found in the numerators. Okay? You'll solve for x in your numerator, and that will give you your x-intercept. So you'll get a number, and we write it as a point. So it'll be a number, comma, 0. Okay? We don't say x equals something, because that indicates it's a line. Okay? So if we don't do that, we make sure we write that it's an actual point. Okay? Vertical asymptotes. The graph of f has a vertical asymptote at each real solution of q of x equals 0. Where is q of x? Our denominator. So that is still a thing. We still solve for x in our denominator. There we go. So each piece of our rational function gives me something, okay? Next is horizontal asymptote, okay? So this is when the degrees start to change. That's going to change some rules with our horizontal asymptotes, okay? When we're not adding something on the end, okay? Because usually if there's like a plus 2 on the end, we're like, oh, it's at y equals 2, okay? When we have it written as polynomial divided by polynomial, it's all about where the degrees are, okay? So my top degree is m, my bottom degree is n. So if my top is less than the bottom, okay, it's going to be y equals 0 as a horizontal asymptote, okay? I've made up some Douglas math, okay? You won't find it in a book. I've purely just created this to hopefully help you remember what does what, okay? When the bottom degree is bigger, it's so big that it reaches up and it hugs the top, and it becomes y equals 0. So that's my quote, hug. Okay, y equals 0. Okay. When my degrees are exactly the same, that's kind of what we ended with the other day, okay? That's when we do our leading coefficients. So that was the a over c. Remember doing that in the previous notes? It was just your leading coefficients. All right, and then if my top degree is bigger, okay, the graph has no horizontal asymptote. I call this the crush. The top degree is so big, it's so heavy, it crushes out the bottom. I know. Again, there's no like mathematical reasoning behind any of those, but I'm hoping it helps you remember which one does what. Okay. So we're going to do an example of each one of those. So we're going to do 3 graphing examples, and then we have 1 word problem today. Okay, just see just what that looks like, how it affects certain pieces, and then we're going to talk about domain and range, and remember all the different ways you can write domain and range. All right, because we have set builder notation, interval notation, inequality notation, all kinds of stuff. All right, so the first one we're going to practice is when my m is less than my n, which is when our bottom degree is bigger. So see how I have 6 divided by x squared plus 1? My bottom degree is bigger. My top degree is 0, technically. My bottom degree is a 2. Okay? So right away, what's my horizontal asymptote? It's going to be y equals 0. This is a hug right here. So we're still at the x-axis. Okay, here's our y equals 0. Okay, let's look at some new stuff. X-intercepts came from solving for x in my numerator. What is my current numerator? A 6. So do I have an x to solve for? No. So guess what? No, it's not 0. It's none. You can graph 0, right? So don't say 0. 0 is an actual number I could put a point on. So there's no x-intercepts. Hey, doesn't that make sense? Where's your horizontal asymptote? The x-axis. So guess what? You can never touch the x-axis, so you're never going to have an x-intercept. Those go together. I know, crazy, crazy. So those will always go together. Okay? Vertical asymptotes. We're going to come from solving x in my denominator. So what is my current denominator? X squared plus 1. So I'm going to take x squared plus 1 and make it equal to 0. I'm going to subtract 1 over. And then we have to square root both sides. Okay? Hold up. Look up here, friends. Where does it say? We're doing vertical asymptote. Look. The graph of f has a vertical asymptote at each real solution. Right? So, if I don't get a real solution, do I have a vertical asymptote? No. Okay? We end up equaling a non-real number, so, I mean, I know it's I and negative I, but we don't graph that. Okay? We are only looking at real pieces here. Alright, so we're about to see a graph we haven't seen before. It doesn't have a vertical asymptote, it only has a horizontal asymptote. So what's that going to look like? I do domain and range after I graph it, personally. Okay, I need to see it. So let's put this into a calculator, plot some points. Remember to put parentheses around it to show it's a fraction. Also put parentheses around your denominator to show that that's grouped together. Okay, handhelds or Desmos. I'm going to put Desmos up here. 6 divided by x squared plus 1. I will say another nice thing about Desmos is it does do the fraction pretty nicely for you. So we have 6 divided by x squared plus 1, and it looks a little something like this. Right? Remember, we can even graph our horizontal asymptote if you want to. If you want to graph y equals 0. I'm going to do a new color. Y equals 0. There we go. We can even graph y equals 0, and it shows me how it's approaching the x-axis but not actually touching it. Even though it looks like it does not. All right, let's plot some points. Let's do a little bit to the left, a little bit to the right. Again, in Desmos, I can push this wheel to show me the table, and I get some points I can plug in. Okay. So I am going to use the values -2 and 1.2, -1.3, 0.6, 1.3, and 2 and 1.2. If you use different points than I do, it's okay. They're all still points on the same graph, right? We're going to get the same thing. People were picky about the next one last class. I don't care what you use. Just put points on there. Okay. So when I graph this, -2, 1.2, -1, +3, 0.6, 1.3, and 2 and 1.2. It's like a volcano or something like that. Okay. My domain this time. Is there anything stopping my graph moving from the left or to the right? Nothing is stopping it. Do I have any breaks or any gaps? No. So what is our domain going to be? All real numbers. Okay. So we can say from -infinity, that's an ugly infinity. Let's try that again. There we go. So +infinity, you can say all real numbers, which is a double-lined R. By the way, that's not IR. A lot of y'all keep putting an I and an R right here. That's not what that symbol is. It's an R with 2 lines. Let me give you instructions. Ready? 2 lines. You come from the back and make an R. In case anyone needed that step-by-step instructions on how to create that symbol. Okay? Either one works for me, though. All right, my range. Is anything stopping my graph from going up and down? Yes, I have a horizontal asymptote, correct? So I can't go below 0. Is anything else happening? There's a little curve, right? So it doesn't go up forever. It only goes up to what? To 6, then it comes back down. But it's not just less than 6. It's less than 6, but it's also equal to, but it's also, I heard over here, greater than 0. Yes. So it's in between 0 and 6. And we are allowed to be equal to 6. That's an actual point on the rational function. Okay. If you wanted to do interval notation, you would do parentheses, 0, 6, and then a bracket. So those both are showing the same thing. So that's inequality notation, and then it's interval notation. Questions about my first graph? All right. Then let's go to graph number 2. Our second graph today is going to be 2x squared divided by x squared minus 9. We're dealing with polynomials now, okay? A big thing that we have to be able to do with polynomials is factor them, okay? And it is going to be extremely important after spring break when we are adding, subtracting, multiplying, dividing, and solving these, okay? Y'all listen, factoring is key. You have to be able to factor, okay? So looking at this guy, can I factor 2x squared? No. Can I factor x squared minus 9? Yes, that's a difference of squares. So we're going to go ahead and factor it. Okay? So 2x squared is still my numerator, but our denominator factors. Do you remember how difference of squares factor? There you go. Plus 3 minus 3. We have to factor because if things cancel, that's going to mean something else. They're not going to cancel today, but they will eventually cancel, and that's going to do something. Okay, so we have to factor. Okay, now x-intercepts. Do I have one this time? Yes. Where is it going to be? It will be at the origin, right? Take my numerator, which is 2x squared. Make it equal 0. I divide by 2, still 0. I square root both sides, and still 0, right? So our x-intercept is at the point 0, 0. Okay? Make sure we write it as a point, not as a line. I'm going to go ahead and plot that too. Okay? Next, my vertical asymptotes. Do I have any? It comes from our denominator. Do we have any vertical asymptotes? Yeah, we do. We have 2 of them. Do you see that? They're at x equals negative 3 and x equals positive 3. I had 2 pieces in my denominator. If you went from the original, x squared minus 9 equals 0, if you add 9 and then square root 9, you would get positive and negative 3 that way also. So going from your original or factored form, you get the positive and negative 3. Okay, so we have 2 vertical lines that we cannot cross. There we go. All right, how about a horizontal asymptote this time? Does that exist? My degrees are the same this time, so what do I do when my degrees are the same? Divide our leading coefficients. So what's my leading coefficient in the numerator? 2. What's leading coefficient in the denominator? So what's 2 over 1? It is 2. Yeah. Looks almost like a tic-tac-toe board. Almost. We only have one horizontal asymptote, though. Okay. So we're going to have 3 branches this time. We're going to have a left piece, a middle piece, and then a right piece when we do it. Okay. When you go to graph it, you can graph your original or you can graph factored form. It's totally up to you. I would suggest doing your original. Okay. So graph 2x squared divided by x squared minus 9. We're going to do a couple points to the left of -3. We're going to do a couple points in between -3 and +3. And then a couple points to the right of +3. I'm choosing these numbers. If you want to choose different points, you can do that as well. I'm just trying to spread it across the whole graph. All right, so are you getting something like this?
Yeah.
Yeah? So did you see the 3 branches? Yeah. Yes? Remember, you can also graph your asymptotes if you want to. You can graph x equals 3. You can graph x equals -3. You can also graph y equals 2. And you can see all of those on here as well. Desmos, you can change the colors, by the way, if you just like hold down on the circle. Wait for it, maybe. Okay, well, it's not doing it for me, but you can. If you hold down on the color circle, you can change the colors. All right, so we have my 3 branches. So -7 gives me a point of 2.45. -5 gives me a point about 3.13. -2 is -1.6. So I'm going to graph those real fast. -5, 3, negative. Oh, that was just those 2. Just kidding. I went too far. -2 is -1. It's down there. We know 0, 0. That was the x-intercept we found, right? Which is also the origin. And then 2 goes back to -1.6. This gives us a little parabola shape down here. And then 5 gave me a value of 3.13. And 7 gave us a value of about 2.45. Like that. So first time seeing 3 branches. Yes, sir. 3.13. There we go. Okay. Let's talk about domain and range. Is anything preventing my graph moving left to right? Yeah, I got 2 things, right? Yeah, I have 2 vertical asymptotes. So my x's can be everything except those. So this is when I like to use set builder notation. Because I can say, hey, it's all of my x's except x cannot equal positive or -3. That's set builder notation. On the board up here, this would be interval notation. So you would do it for each branch. So you could say -infinity to 3, to -3, excuse me, -3 to +3, and then 3 to infinity. So this is interval notation of showing the domains of each branch. Remember, no brackets because you can't equal to them. And then my range, everything except what? Everything except 2. So set builder, I'm going to say all of my y's except y cannot equal 2. Or interval notation, you could say -infinity to 2 and then 2 to infinity, showing that jump in your y values. I'm showing you all the ways because you're going to see all the ways on Big Ideas, on SATs, pre-cal uses all these different notations, so I want to make sure you're familiar with them all. What's that? The little bit in between. Oh, this gap between 0 and 2? I guess we could. Yeah, I would say so. So what, between 0 and 2? That's a good observation. Yeah, let's say, Did y'all see what Kale noticed? There's a gap between our x-intercept and our horizontal asymptote. So it's everything except between 0 and 2. So what if we said all y's have to be less than or equal to 0, right? And my y's have to be greater than 2. Does that make sense? Okay. Good job, Kale. The student becomes the teacher. Good. So if anyone's confused, he noticed the gap right here. That there was no function crossing over, and there won't be a function crossing over. Good job. All right, ready for the back? Yeah? Okay. All right, now we have x squared plus 3x minus 4 over x minus 2. What did I say you need to get used to doing with all of these? Factor if you can, okay? We have to factor quadratics if we can. So can I factor x squared plus 3x minus 4? Yes. How does that factor? X plus 4 and x minus 1. Our denominator of x minus 2 does not factor anymore. You cannot cancel anything. Don't go in there and start crossing off x's. No, no, no. Okay? There's a reason why I put parentheses. Parentheses means they're grouped together, right? You can't separate them. So if I had 2x plus 4's, that's a common factor. Yes, I could cross that out. Okay? But you can't just start crossing off x's because you feel like it. Or doing, 4 divided by 2. Nope, it's not 4 divided by 2. It's x plus 4 over x minus 2. So be careful. Don't do it. All right. It's in fully factored form. I can't do anything else to it. So now let's look. Do I have any x-intercepts? Yeah? What are they? Yeah, I got 2 of them, right? So we have the point -4, 0, and the point 1, 0. Do we have a vertical asymptote? Yes. It comes from what piece? Our denominator. So if I have x minus 2 equals 0, we get x equals positive 2. How about our horizontal asymptote? Ooh, why not? My degree up top is bigger, right? So it crushes it out. So I don't have one this time. All right. So let's plug in some points to the left of 2, plug in some points to the right of 2. You can use the ones I use. You don't have to. I like to try to spread it across my graph, so I used these. 0, 1, and then 3, 4, 8, and 12. Those are the points that I used. I already know this one, right? Boop. My x-intercepts. I already know those. All right, so let's plug it in and see what it looks like. All right, we have x squared plus 3x minus 4 divided by x minus 2. And it looks like this. I know. This is a really good one to see. So like these used to be lines. Look, if I zoom out, can you see like it used to be a line? But what broke it? The vertical asymptote broke it. So that's why there's a bend and a break in the middle. Math is cool sometimes. Sometimes. I said sometimes. Okay. So let's get some points to plot. I got -8, gave me -3.6. We know -4 is 0. 0 gave me a value, y-intercept of 2. And then we have our other x-intercept at +1. That's the left branch. The right branch started off with 3, which gave me a y value of 14. 4 gave me a y value of 12. 8 gave me a value back at 14. And 12 gave me a y value of about 17.6. So we get that piece. Okay. All right, my domains and my ranges. Let's see here. Domain is my x values. Is anything stopping my graph going left to right? Yes, what's stopping it? That x equals 2. So we can write a couple ways. I can say all of my x's, except x cannot equal 2. I can say x's have to be less than 2, and x's have to be greater than 2. These are all the same thing. We can say -infinity up to 2, and 2 to infinity. 3 different ways to say the same thing. 3 different forms. We have set builder notation, inequality notation, and then interval notation. Okay. My range. Did anything stop my y's from going up and down? Well, nothing stopped it, right? But you do see that we have pieces missing, right? There is a gap, which kind of links to the problem we did before. Kale noticed there was a gap in between the 0 and the 2. There's a gap happening here as well. I zoomed way out on that one. There's a gap happening. Do we agree? Between 2 and 12? There's just no y's being used between 2 and 12. So we can say we're going to do all y's that have to be less than 2. We can be equal to it. And my y's have to be greater than or equal to 12. We could say -infinity up to 2. Ooh, and they should get brackets, right? Yeah, we can bracket here. And then we can bracket and say from 12 and above. Set builder notation would get a little messy, to be honest, with this one. So if you want to show a gap, I would do something like this. This piece, and then you can jump and then go over here and do this piece. Good? Good on questions? Or graphs, not questions. Then we're going to do our word problem with the pool and the patio and all that goodness. I know, right? We're trying to minimize our area so we can, use as much as we can technically without wasting. Minimize the usage so you're not wasting space. Any questions before we go to the pool? You brought your swimsuits, right? There you go. Okay, here we go. You are designing a rectangular pool with a patio along the perimeter as shown below. You want the area of the pool to be 300 square feet. Find the dimensions of the pool that minimize the total area of the pool and the patio. Okay? So we have two areas we're going to work with. Area of the entire thing and then area of just my pool. Okay? So let's figure out the area of my entire patio situation. So do we agree? Would you say that the length, this is y, right? So is this y plus 8 plus 8? Do you agree with that? And then how about the width? Yeah? So we can say that the total area, I don't know why I put it over there. I don't know what I'm doing, guys. So our total area, sorry, is going to be x plus 12 times y plus 16, because we do length times width. Or width times length. Doesn't really matter, does it? But we usually write our x's first. If you have y plus 16 times x plus 12, you're not wrong. You're okay. The next area that we need to work with, because it did tell me something. It told me the area of the pool. You want the area of the pool to be 300 square feet, right? So my pool is x times y. Well, I know it's going to be 300, right? Okay, so we need to use the information we have been given to find what they're asking of me, okay? Find the dimensions of the pool that are going to minimize the total area of the pool and the patio, okay? So we need to use the fact that we want our pool to be 300 square feet into my total area to then help me minimize the entire piece, okay? So how am I going to do that? I'm going to solve for either x or y so I can plug it into my total area, okay? We usually like y by itself, so I'm going to solve for y here. Divide both pieces by x. So I'm going to use the substitution that 300 divided by x equals y. And I'm going to use that to substitute it for the y in my total area. Because if I have just one variable, I can work with that, I can solve, I can graph. Okay? So our total area, okay, is going to equal x plus 12 times 300 over x plus 16. And this is going to be, it's a new function, so we have a new y and a new x. This is all being related to our total area now. Okay? So use what you know to find what you need. We are going to multiply, and it's not as crazy as you think, I promise. So we'll do first, outer, inner, last. First, x times 300 over x. Well, that's nice because it's just going to be 300. X times 16 is 16x. 12 times 300 over x, you do 12 times 300 and then divide it by 1 times x. So 12 times 300 is 3600. And 1 times x is x. And then 12 times 16 is 192. Looks a little messy. I'm going to combine like terms that I have and write it in the right order. So we're going to say that the total area of my patio and pool is going to be 16x plus my constant of 492 plus my remainder of 3600 over x. Okay? We've created a rational function that we're going to graph and find the minimum of. Okay, it's going to give me the minimum dimension of the pool. Okay, so we are going to graph it. It's going to look something like this. I'm just going to go ahead and warn you. Okay, but let's graph it and look together. Make sure everyone's done. Okay. You okay? Alright. So I'm going to go into my Desmos. Alright, so I am going to graph. Where's my equation? Okay, 16x plus 492 plus 3600 divided by x. Okay. So it looks like you have just the parabola, but Desmos people, you can easily pinch, right? Because none of that would make sense, correct? I can't have negative dimensions. It does not make sense. All of those are going to be negative somehow. Don't like it. I have to have positive values. Oh, look, there it is. That's what I need, okay? If you have your hand held, I would go look at my table, okay, and see where your y values are going. And I would change your window based off of what you see on your table. Okay, so I would change your window, your Y max to probably be like 1200 or something like that. Okay, with Desmos, again, we like it. I can just tap that minimum point. And it tells me it's 15 and 792. Okay, it tells me it wanted to minimize the area. So that's why I'm looking for the minimum on my graph. Okay. So 15 and 792. Let's come back here and talk about what that means. Okay. So we found our minimum. It is 15 and what did I say? 972. So this is an x and a y, but remember it's the x and the y for my total area. So my x is still the dimension of the side of my pool, right? That y value is the total area. Make your math make sense. Am I going to do a pool that has a side of 15 feet and the other side of 972 feet? No, that math does not make sense. Okay? So those are not going to be the dimensions of your pool. I have the x value of my pool, but this y is referring to the total area because that was the y that we used this entire time. Okay? So that's what this is saying. Okay? But it's not what it's asking me. It wants the dimensions of the pool to minimize the area. I have my x value. I know x equals 15. So to plug it back in for my pool y was 300 over x, right? So I can say 300 over 15. Now that math makes sense. Would it make sense to have a pool that's 15 by 20 feet? Yes, that math makes sense. So the dimensions of my pool need to be 15 feet by 20 feet to be able to minimize the total area of the pool and the patio. Didn't ask, but what would that total area be of the pool and the patio? The 792. That's what that number is representing. When you minimize the area of your pool, that shows you the area of the entire patio. But again, it didn't ask me that. But that's what that number means. I want to make sure you knew what that meant in context. Okay? So you're like, what do I write? You write this. The dimensions of the pool that minimize the total area of the pool and patio are going to be that x equals 15 feet and y equals 20 feet.